So good evening all. Am I audible? Hello. So good evening all. Welcome to the fourth session, problem solving session for the course Geotechnical Engineering 1. I am Yogendra Narayanan. I am a PMRF research scholar who will be taking these sessions. Uh, to give a brief introduction about this session since it is being recorded. So these sessions are intended to make the learners proficient in the subject by making them solve the questions each week based on the contents of that particular week, uh, so that they get enough confidence and exposure and an idea to approach the problems that will be asked in the uh, NPTEL final examinations as well as your university examinations and the competitive examinations. So it provides a way to clear your basics and a form of a revision uh, of the concepts that has been taught in a particular week. So these sessions are conducted on Saturdays usually from 5 p.m. to 7 p.m. and the previous assignment questions and some previous asked questions will be solved. You will be solving along with me, and you are free to interrupt whenever you want, and uh, you can also reach out to me via email or NPTEL sessions in the website, NPTEL website, in the portal in the NPTEL website. So these recorded sessions will be uploaded in the YouTube, and links will be shared with you, and the slides also will be shared with you. So I request or I expect the participants to be on time, which most probably are not, and attend regularly. And while attending these sessions, please refer to the contents of the week before coming here, as this session is not necessarily another teaching session. So it is just a revision session where the already taught concepts are being practiced in the form of numericals or conceptual questions, etc. So in this week, to give a glance of what has been covered, so the lecture start this week covered the initial properties of soils, weight and volume properties, and how to gauge its density, measure what are the types of density or type of unit weights, what is some fundamental parameters of defining a soil mass, all right, and how to analyze the particle size distribution curves, and that is the basis for understanding the soils, uh, by which a basic classification is done conventionally, although several other modern classification techniques are available, which is not the scope of this course. And with this, from this week onwards, we'll be actively solving numericals, both fundamentally, and I will introduce you to some of the practical applications of of the concepts in in, that can be encountered in the field. Right. So with this, I welcome you to the session. So the course instructor is Professor D.N. Singh from IIT Bombay. Sadian Singh from IIT Bombay. So we'll just share the screen. The screen is visible now. This is the course. We'll be going to the first question. Which among the following has a minimum specific gravity? Which among the following type of soils or mineral or type of soils have minimum specific gravity? Option A bentonite, option B quartz, option C peat, option D clays. So which among the following has minimum specific gravity? Option A bentonite, option B quartz, option C peat, option D clays. Now to understand this, so first of all we will come from bentonites. The range of specific gravity of bentonite is around 2.4. Alright. And quartz it's 2.65. Alright. And clays it is usually 2.7 to 2.8. But there are now some other things. Let me come to that. Peat is usually organic, pure organic soil. So its density, the specific gravity varies. It's around 1.7, around these ranges. So hence, the among the following we have a peat, which is lesser in specific gravity due to the presence of heavy organic nature. All right. So that's why during the measurement of specific gravity or before any other tests, and especially you might have been studied that you might have come across that for particle size distribution also the prior to that treatment is given so that the organic matter is removed completely. So that is the thing. So in the conventional geomechanics, geotechnical analysis of particles or whatever um, index properties that we measure. So the main precursor to conducting these tests is these tests should be free of moisture content and uh, as well as organic matter. So that is the basic requirement of for conducting these tests. So apart from this, now several industrial byproducts which are similar to soils have larger specific gravity, like red mud, which has around more greater than 3 red mud and steel slags, which are inherently denser due to the presence of alumina and steel, which naturally increases its specific gravity. So those things are man-made or byproducts of various industrial processes which are similar to soils. All right, just sorry. There has been a network issue. So coming back to this. So coming back to the second question. So coming to the second question, which is the correct relationship between voids ratio and porosity? Which is the correct relationship between voids ratio and porosity? So now we'll start with porosity equal to, it's defined as volume of voids to total volume. All right. Now this can be written as volume of voids divided by, or it can be written like this: volume, total volume minus volume of solids. Should be total volume. Now 1 minus Bs by P. So, so how do we write this? Is equal to Vb by total V, right? Now Bv divided by Vb plus Vs. That can be written as Vb, take Vb out in common, 1 plus Vs by Vb, right? So this gets cancelled. So Vs, and we know that V is Vb by Vs. So this is going to be 1 by 1 plus 1 by V. So then we know that is equal to V by 1 plus V. So this is the relationship, right? So the right option is A. Now coming to this, let's extend this discussion to a bit. So wherever where, in soil mechanics, apart from porosity, porosity is a term usually people try to understand easily. But however, the term voids ratio is used widely to determine the state of the soil. Why? Can if you think about this reason, you have to come to the basic definition. So why voids ratio is used? And initially, um, uh, for example, in rocks and everything, porosity is the term which is widely used. But in soils, the term porosity has a disadvantage. So what is that? Is once we change the volume of voids, and we know that the volume, total volume is the summation of volume of solids plus volume of voids, right? So once we change this, the total volume is also going to change. So whatever parameter which we are trying to study here, we are trying to study a parameter which is variable, that is ideal parameter. How is is if you look it at a mathematical point of view, it is a relative parameter, the variation of a parameter with respect to another. Now, for understanding this relative variation, you need the basic parameters, that is the independent parameters should be non-variant. That is, it should not vary with any other, uh, that is, it should be a constant. It should not vary with any other changes to any other changes to some other parameters. Now, but here we note that volume of voids, once we change this volume of voids, it is getting reflected in the total volume also. So the numerator is also changing and the denominator is also changing. So it is not a correct representation of a relative parameter. That is a relative parameter uh, for defining the state of the soil. But if you see, the parameter which is getting constant here is the volume of solids. You have specific number of grains in a particular volume. The way you compact it is going to change the total volume. Otherwise, the volume occupied by the solids, that is the grains, is going to be constant. So then it makes more sense to define a term where the volume of voids is uh, defined with respect to volume of solids, which is not a variable for a particular volume, total volume, right? So, hence, if we see this parameter, volume of solids is not going to change; it's a constant. And if even if volume of voids is changing, volume of solids is not going to change. So, hence, it is a relatively advantageous ratio to define the state of the soil. That is why wherever in soil mechanics to explain the state of the soil, we use the term voids ratio instead of porosity, right? So that is a small thing which I would like to clarify, and hope this derivation is clear. It's fairly simple. So coming to this the next question. In which type of soil does core cutter method is preferred? This core cutter method. Which type of soil does core cutter method is preferred? Option A, cohesionless soil. Option B, cohesive soil. Option C, both cohesionless and cohesive soils. Option D, none of the above. Right? Now, core cutter method, how it is done is you have a mold. There is uh, where it is the sample is collected of a fixed volume. You have a mold of fixed volume where you place it and you just insert it to the ground. And once it is completely inserted, you just take uh, the, the core out containing the soil. So, and you measure the weight of the soil and you know the volume of the mold, and you can get the weight by volume, you can get the bulk density of the soil that is there. However, this uh, the major requirement for this core cutter is the soil. Once you press the core cutter deep inside the soil, and once you remove, you once you are still we have to take that. So there should not be any loss in soil, which which can result in fatal errors in calculation of bulk density. Hence, this method is purely utilized for cohesive soil, where the soil remains intact without even if we remove the support. You get a chunk of soil, and it once you press the core cutter to the ground, to a large extent it gets stuck. It occupies the entire volume of the core cutter. Hence, relatively, core cutter method is preferred for cohesive soils. And there is a method of sand replacement where you take out the amount of soil, and you know that you fill that you fill the amount of soil taken with respective with an amount of sand. You know the mass of sand that is being used, and you know the specific gravity, so that you will know the volume of sand um, that you are going to use it to cover the pit that you have created. So that is known as sand replacement method. So that is both useful for cohesive and cohesionless soil. Sand replacement method, cohesive and cohesionless. Apart from that, now several non-invasive techniques have come for density measurements, like you have neutron density, uh, etc., and some acoustic and electrical methods where you can determine the density of the soil and the layer of the soil deep inside the ground. You can determine the layer uh, that is to what thickness a particular type of soil is present. So those things can also be mapped. You can practically map the subsurface. So the techniques, field scale techniques have been developed for these purposes also. So the more conventional techniques are cohesive and questionless. Apart, since you since you are being introduced to this the subject, it is necessary for you to learn. Back to this. So that's what we have been talking about the, the field scale techniques. As I was mentioning, there are several non-invasive techniques which have been developed to map the entire subsurface itself based on several contrasting parameters like water content, density, etc., and nature of pore fluid, etc. Now, coming to the fourth question. Coming to the fourth question. The voids ratio of a sand is 0.7. What would be the relative density of it if the minimum and maximum voids ratio are 0.55 and 0.90 respectively? So they have given E as they have given E as zero point 0.7 and E min is 0.55 and E max is 0.90, right? Now we have to calculate the relative density. dr is given by the formula V max minus E divided by V max minus E min. So this is also a relative parameter, that is where for a particular type of soil, for a particular grain size, so Emax and Emin remains constant. So you can refer corresponding IS codes for determination of Emax and Emin. So it's usually fluviation technique where we determine the Emax, and for Emin you usually uh, use the shake table to vibrate to for the soil particles to settle down completely, and you measure the weight and volume and the calculations, usual calculations. And this parameter of relative density is exclusively for coarse grained soil or cohesionless soil or granular soils. All right. So the where the grains are individualistic and not they are not plastic in nature. And coming to this problem once again, Emax is zero point 0.9 minus actual voids ratio in the soil is 0.7 and Emax is zero point 0.9 again, and E min is 0.55. So when we subtract, it comes to 0.2, and this it comes to 0.35. So now calculating this, 2 divided by 0.35. So it's almost 57 percentage. It comes to around 57.14, which can be approximated as 57 percentage. And these parameters essentially should be rounded off. Uh, uh, there should be no decimal places as such. It should be rounded off, as it is a usually it is a ratio where we round off this decimal to two places, and hence the percentage should be expressed in terms of whole number. All right. So the right answer is 57 percentage. All right. Any doubts? This question. Next question. Coming back to the next question. A soil in its compacted state has the following properties. Porosity is 0.375, degree of saturation is 0.09, specific gravity is 2.65, and its water content is, and they're asking for gravimetric water content. So if the term water content is used, ideally it refers to Sorry for the inconvenience. The internet connection is really poor here. So coming back to this, we have when the water content, the term water content is mentioned, it usually refers to gravitational water. All right, gravitational or sorry, it's gravimetric water content. Gravitational water. You will learn this term in the coming lectures in the 3 4 weeks. So it is gravimetric water content. Gravimetric water content. All right. Now, so we know the universal relationship SE is equal to WG. All right. So we know the saturation 0.9. We E is there. We know the specific gravity, which is 2.65, and W. So we need to calculate W, right? Now, coming back to this, we need for calculation of W, we need the void ratio. But we have a void ratio in terms of porosity, which is 0.375, all right, which is equal to E by 1 plus E. So now solving this 0.375 plus is equal to E into 1 minus 0.375, which gives you 0.375 by 1 minus 0.375 is 0.625. Right? Now calculating this, 375 divided by 0.625. Its the void ratio is 0.6. Now it's going to be zero point 0.9 into 0.6 divided by 2.65. Now calculating this, we have into 0.9 divided by 2.65. It's going to be 0.2033, which is approximately 0.20 when rounded off to two decimal places. It's going to be 20%. All right. Now the answer is option B. Any doubts? Now the same question, what is the dry density of the soil mentioned in the previous, that is from the previous question. Gamma D, gamma D, we know that it is defined as gamma W G divided by 1 plus E, right? It's usually it's G plus Se. For dry density, saturation is going to be 0. And so it's usually 0 and it gives you a W. And now let us take gamma 1 as 1. So it's gram per cc. So it's 1 gram per cc. So this GS is 2.65 divided by 1 plus zero point 0.6, which is going to be 2.65 divided by 1.6. How much is it? 0.65 divided by 1.6. Going to be 1.65. 1.656. Rounding off to two decimal places, it's going to be 1.66 gram per cc. Alright. Okay, if you want to convert it to kg per meter cube, then just multiply it by 9.81. Right, so that is the dry density. Back to the next question. Coming back to the next question, what is the size of the silt? So what is the silt size? Silt size. So we know this less than 2 microns is going to be clay sized. 2 microns to 75 microns is going to be silt. 75 microns to 4.75 mm is going to be sands, right? Now silt size varies from 0.02 microns is nothing but 0.002 mm, and 75 micron is nothing but 75 micron is nothing but 0.075 mm. So the range is going to be option C, right? So coming to the next question, why H2O2 is added? Why H2O2 is added into the soil before performing hydromet analysis? So option A, to prevent clogging of soil particles, option B, as a dispersing agent, option C, to remove the organic content, option D, none of the above. So H2O2, to understand this, we need to understand what H2O2 is. As you might have studied in your 10th and 12th chemistry, H2O2 is a strong oxidizing agent. Oxidizing agent. So, and we also know that for the particle size analysis, we need to remove the organic matter. So one of the best ways to remove the organic matter is by adding, either it is by heating, which requires more than you have to go to higher temperatures, like more than you have to heat it at 440 degrees centigrade. Otherwise, use some oxidizing agent, which is usually hydrogen peroxide, or which is commonly used as an oxidizing agent in chemistry, and it can be added to the soil to uh, to decompose the organic matter by oxidizing it. Hence, H2O2 is used to remove the organic content from the soil as it is a strong oxidizing agent. Alright, now coming to the next question. Both the questions are answered. Now, just a minute. Coming back to the next question. Coming back to the next question. So, which among the following statement is correct? Incorrect. Which of the following statements is incorrect? So, option A, meniscus correction is always positive. Option B, temperature correction is negative when the soil solution temperature is below the calibrated temperature of hydrometer. Option C, dispersion agent correction is always positive. Option D, both A and B. So, to understand this, you need to understand the uh, how to the exact term is how the hydrometer is marked. So hydrometer usually has this cylindrical or narrow cylinder with a bulb at the bottom, lead bulbs. So so the demarcation is like this. So it starts from 0.995, let us say, and it's 0. Sorry, it's going to be 1.000, it's going to be 1.005, 1.010, 1.015, and 1.020. Usually it extends up to 1.025. and this goes up to 1.030. Now, let now there are three possibilities in this. Once you insert the hydrometer into the uh, slurry, that is soil slurry. So let us consider this is the soil slurry which you have prepared. All right. Now this is inserted into this. I'm just drawing a. Now, due to the surface tension, there is a meniscus that is formed. All right. So this is the graduations in the. So graduation is the right term. Graduation. So now, if I zoom this portion and see, it forms a. It comes here and it forms a meniscus due to the surface tension. So the actual reading which you take, so it corresponds to 1.005. But the actual reading is, which is the visible is 1.00, and the actual reading which you take is 1.005. So the meniscus, since it is usually water, the meniscus is usually towards upward. So hence the correction needs to be positive. So actual reading is, for example, actual reading is, so sorry, apparent reading, apparent reading is 1.00, and actual reading is 0.005. So the correction is always positive. Alright, you should add. The correction is positive, the error is negative. The error is negative and the correction is positive. Alright, so this statement is always right. Now, temperature correction is negative when the soil solution temperature is below the calibrated temperature of hydrometer. Now, once the temperature of the solution is more than the calibrated temperature, the water level will be more. This is T ideal, this is T greater, and this is T lesser. Now, T greater is due to the expansion and contraction of the fluid, that is the water bath. Now, once the temperature is greater than the calibrated temperature, the correction tends to be positive. You should add the values. Once, if the temperature is lesser, actually the reading should be this one, but you get the reading, but you see the reading as 1.010, and the correction has to be negative. So for the temperature correction, if the soil temperature is less than the calibrated temperature of the hydrometer, then the correction needs to be negative. So this statement is also right. So coming to the third option, dispersion agent correction is always positive. So once you add this dispersion agent, it tends to increase the density of the solution, which results in the dipping. So as you know, the how to put, uh, as uh, as time progresses, it tends to the hydrometer tends to dip as the particles settle, right? So it tends to dip, and if the density of the fluid is more, it tends to dip more. So hence the the reading which you see due to the dispersion agent is this one, and for example this one, and the actual reading should be this. So this correction is always negative. So dispersion agent correction is always negative, hence this statement is incorrect. right? Mhm. Right. So coming back to this question, if soil particle diameter decreases by a factor of 2, what will happen to the settling velocity? So this is related to Stokes law, where the velocity is directly proportional to particle size, the square of the particle size. All right. So V1 by V2 is equal to V1 square by V2 square. All right. Soil particle diameter increases by a factor of 2. So now V, that is V2 is equal to D1 by 2. So V1 by V2 is equal to D1 square by D1 square by 4. V1 is going to be 4 times of V2. Alright. So that means V1 is more, V2 is less. So V2 is equal to V1 by 4. It's going to decrease 4 times. Alright. So the option D is right. Moving to the next question. What is the relationship between sphericity, roundness, and rigidity? So usually there is a these are all statistical formulas. So the rigidity is equal to sphericity plus roundness by 2. These are statistical formulas. You can refer to the lectures of how this has been derived. So S plus R by 2. This is the right option. Now coming to question number 12. The air content of a soil mass at complete saturation is. So we know that air content plus saturation is equal to 100% or 1. Sorry for the inconvenience. Uh, Sorry for the inconvenience. There is a small network issue. So we were there at the air content is air content plus saturation sums up to 100% or in fraction it is 1. So complete saturation in the sense SR is equal to 1 or 100%. So in this case, air content is going to be 0. So the right option is option C. Middle. So coming to the next question, the dry unit weight of the soil fill is found to be 15.8 kilonewton per meter cube. The specific gravity of soil solids is 2.65. The maximum and minimum voids ratio determined in the laboratory are 0.88 and 0.42. The relative density of the soil is. So now we have, so first we'll write what is the formula for relative density. Now we have E max minus E divided by E max minus E min. Right. Now we know E max as 0.88 minus E divided by 0.88 minus 0.42, but 0.42. Now we have to compute E. For computing E, what we have is we have dry density 15.8 kilonewton per meter cube, and you have soil solids specific gravity which is 2.65. And how can we relate this? Gamma D is equal to gamma W G divided by 1 plus E. So we know that 15.8 is equal to gamma W, let it be 9.81 into 2.65 divided by 1 plus E. So which is going to give this 1 plus E is equal to, calculate this ratio. So back to the calculator. So 9.81 into 2.65 divided by 15 point, it's 1.65. It's approximately 1.65 and E is going to be 0.65. Now coming to the computation, 0.88 minus 0.65 divided by 0.46. Now computing this, the 0.88 and 0.65 divided by 0.46. So approximately it's going to be 52%. And this slight 1 or 2% is due to the value of gamma W which we have taken. So you can also try with 10 instead of 9.81. So that's not going to be an issue because you can always write in your answer script that you have assumed this value of gamma W. Most probably, in most cases in your examinations, you will be provided the value of gamma W, which should be used in your computation to avoid this confusion. All right. So I hope this part you understand. So coming back to the next question, uh, soil sample is found to have a porosity of 0.25. G is 2.65 and water content of 15%. Can the soil sample exist in this state? Exist in this state. What are all the details we have? We have porosity 0.25. We have G, and in this case we have E, which is uh, which can be derived, which is n minus 1 minus n by 1 minus n, which is 0.25 by 0.75, which is 0.333, right? Or 0.33. G is we have 2.65 and gravimetric water we have 15%, which is 0.15. So the fundamental equation is SE is equal to WG. Now let us calculate saturation first. Saturation is 0.15 into 2.65 divided by 0.33. So it's always going to be greater than 1, which is not at all possible. So saturation is always less than or equal to 100%. So which actually fails the condition. Hence, soil cannot exist in this state. Soil cannot exist in this state. So you can write as not possible. Now coming to the next question, density and water content. Density and water content of a soil specimen retrieved from the field are 18.4 kilonewton per meter cube and 8% respectively. The maximum and minimum dry density is 20 kilonewton per meter cube and 16 kilonewton per meter cube respectively. So what is the dry density of the soil mass? First question. So let us list down what are all the parameters we have. We have gamma bulk at the field, which is 18.4%. You have water content, which you have 8%. You have gamma D max, which corresponds to E minimum is 20 kilonewton per meter cube. And you have gamma D minimum, which corresponds to E max, which is 16 kilonewton per meter cube. Now, the first question is dry density of the soil. Gamma dry, we also know we have the formula of gamma bulk by 1 plus W. So we have 18.4 plus 1 plus 0.08. So we have 18.4 divided by 1.08. So how much is the thing? 18.4 divided by 1.08. It's going to be 17.04. 17.04 kilonewton per meter cube. Alright. So now we are know that V max minus E divided by E max minus E min. And also we know that E is inversely proportional to gamma D. So this once we cancel out the ratio, we can write as E max corresponds to 1 by gamma D minimum minus 1 by gamma D divided by 1 by gamma D maximum minimum minus 1 by gamma D maximum. So what we get is 1 by 20 minus, sorry, minimum, right? So 1 by 16 minus 1 by 17.04 divided by 1 by 16 minus 1 by 20. Now calculating it, dr we get as 1 by 16 minus 1 by 17.04 divided by 1 by 16 minus 1 by 20. So around it's going to be 0.305, which is 30.5 percentage, 31% approximately, 31%. So the dry density of the soil is 17.04 kilonewton per meter cube, and the relative density is 31%. All right. I hope it's clear. So now coming back to the session to the next question. So if the voids ratio of the soil sample is 0.35, what will be its specific volume? So specific volume. Right. Now, what is meant by specific volume? Specific volume is nothing but volume of the soil sample when Vs is equal to 1. So the phase diagram, you have volume of voids, you have volume of solids, right? So when this is equal to 1, E is going to be Vv, right? So the total volume is going to be 1 plus Vv, which is going to be 1 plus E. So specific volume is 1 plus E. In this case, it's going to be 1 plus 0.35 and going to be 1.35. Alright, so it's going to be Cc. So 1 is 1 Cc and it's going to be 0.35 Cc of 1.35. Alright, assuming the shape of the grains to be spherical. Coming to the next question, assuming the shape of the grains to be spherical, the voids ratio corresponding to the loosest state would be. The voids ratio corresponding to the loosest state would be. So for the loosest state, the arrangement is rectangular arrangement, right? This is the arrangement. So this is 4. If you have another 4 back side, you will get an entire cuboidal arrangement. It's called a can be rectangular or cuboidal arrangement. So let us consider a unit cube, which consists of 1 cube is equal to 8 grains or 8 spheres. Right now, the dimension is going to be the side of the cube is going to be this one, which is going to be, let us take the dia of sphere is equal to d. So this is going to be 2d. Now volume of sphere is equal to 4 by 3 pi d by 2 cube. Alright. So the total volume occupied by the grains is total is 8 into 4 by 3 pi d cube by 8. This gets cancelled out. 4 by 3 pi d cube. And the total volume is going to be 2d into 2d into 2d. It's going to be 8d cube. Now what we know is we need voids ratio. So E is equal to VV by Vs. And we know that V minus Vs by Vs is going to be 8d cube minus 4 by 3 5d cube divided by 4 by 3 5d cube. So d cube gets cancelled everywhere. It's going to be 8 minus 4 pi by 3 divided by 4 pi by 3, which comes approximately to 0.91. So the Voigt's ratio at the loosest state would be 0.91. All right. I hope this is clear. To the next question. Match the type of soil with their maximum particle sizes. Match the type of soil with their maximum particle sizes. So clay, it's going to be 2 micrometer. Silt is going to be 75 micrometer. Sand is going to be 4.75 mm. And gravel is going to be 75 mm. Now this is the match. So this is fairly straightforward. I'm coming to the next question. Assign the correct type of gradations to the corresponding figures. Assign the correct type of gradations to the corresponding figure. So there are three type of gradation. One is gap graded, poorly graded, and uh, gap graded, uniformly graded, and uh, uh, well graded. Two types are there: gap graded, uniformly graded, well graded. So gap graded is you there is a the variation of the particle size is uniform, but there is no presence of a particular size. So which causes a plateau in the curve. All right. So among this we have a plateau in this. This is a plateau we have which specifies that there is no particle size corresponding to that. So this is gap graded GG. And coming to this second graph, so you see that the there is a sharp big drop in the curve, sharp drop in the curve. So that means all the particles, most of the particle sizes range in a particular size, are present in a particular size. So that means the gradation is uniform. So this corresponds to uniformly graded soil sample. Now here you find a almost perfect S term. So that means there is a wide range of particle sizes that are available in the soil sample. So this, since wide ranges of soil sample sizes are available, so you get a more denser soil sample. So which in turns gives us the classification of well graded. So usually for several engineering purposes, we prefer well-graded soil owing to its increase in shear strength and uh, density uh, and the minimality in voids so that you get the maximum engineering properties out of that. So this is well-graded soils. Coming to the next question. The sieve analysis on a sand sample was conducted and D60, D30 and D10 were determined to be 0.8 mm, 0.4 mm and 0.1 mm respectively. The coefficient of uniformity and coefficient of curvature CC respectively are coefficient of uniformity and coefficient of curvature CU and CC respectively are. Now we have, first we will write the relation of Cu, coefficient of uniformity, which is d60 by d10, and coefficient of curvature is d30 square divided by d60 into d10. So d60 we have is 0.8 and d10 is zero point 0.1. It's going to be 8. d30 we have is zero point 0.4 into zero point 0.4. d60 is going to be 0.8 into zero point 0.1. So this is 2 times. This is going to be zero point 0.2 and this is going to be 2. Right? So Cu is 8 and Cc is going to be 2. Therefore, the right option is option A. So the hydrometer analysis is based on the principle of Bragg's law. We know that it is n lambda is equal to 2d sin theta, which is for XRD. Coulomb's law is for electrostatic attraction. Force is equal to Q1 Q2 by R square some K. Alright, electrostatic. Ohm's law is V is directly proportional to current. V is equal to IR. V by I is equal to R. Sir. And so V voltage is directly proportional to current. That is the Ohm's law. Stokes law we have this relates the force acting on it, uh, force acting on the part uh, on the substance to its settling velocity. So settling velocity is given by gamma s minus gamma w by 18 mu into d square. So gamma s is the unit weight of soil solids, unit weight of soil solids, unit weight of water, and this is dynamic viscosity. And this is diameter of the particle. Comes from the basic Stokes equation where the force acting on the particle traveling with terminal velocity is 6 pi mu d velocity. Right. So this is Stokes law, which on which hydrometer analysis is based on. So the right option is option C. All right. Now coming to the next part. Which of the following chemicals are used as dispersive agents for hydrometer analysis? Which of the following chemicals is used as dispersive agent of hydrometer analysis? Now, a dispersive agent is uh, widely the widely used dispersive agent is sodium hexametaphosphate. So you can find it in any textbook. The widely used dispersive agent for hydrometer analysis is sodium hexametaphosphate. All right. Now coming to the next question. Laboratory sieve analysis. Laboratory sieve analysis was performed on a soil sample using a complete set of 5 standard IS sieves. Out of 500 grams of soil used in the test, 200 gram was retained on 600 micron sieve, 250 gram was retained on 500 micron sieve, and the remaining 50 grams was retained on 425 micron sieve. Compute the effective size and coefficient of uniformity. Now, total is 500 grams. Alright. Now, we have size. There are three sizes: 600 microns, 500 microns, and 425 microns. Right. Now, the second thing is weight retained. So the weight retained is 200 grams, 500 is 250 grams, and 50 grams is passing. Hmm? The 50 grams is retained in 425 microns. So the passing weight passing is going to be 300 grams, it's going to be 250 grams, and it's going to be 450 grams. Right. So the effective size is where 10% uh, 10% is retained or 90% passing, which is 425 micron, which is D10 is 425 microns, and coefficient of uniformity D60 by D10, which is going to be 600 by 425, which is ideally 600 divided by 425, going to be 1.4, right? So that's what is being calculated here. Now, coming back to the next question, last question of the day. So, embankment fill needs 7 lakh meter cube of soil with a voids ratio 0.7. There are two burrow pits, pits X and pit Y, where the required soil can be taken and transported to the site. So, the burrow pit X has a voids ratio of 0.75, and burrow pit Y has a voids ratio of 1.65, and the transportation cost for uh, taking soil from burrow pit X to the embankment location is 20 rupees per meter cube via truck, and for burrow pit Y, it costs around it costs 15 rupees per meter cube, right? costs 15 rupees per meter cube. Now, the question is, what is the transportation cost for pit X and what is the transportation cost for pit Y, and which is more economical? All right. Now, we have to bifurcate this problem into three. One is embankment, borrow pit X, and borrow pit Y. Right. Now, the total volume of embankment is going to be 7 lakh meter cube, and the voids ratio is going to be 0.7. And in this, we need to find, we have the voids ratio is 0.75, and we have in this voids ratio is, let us say Ex and Ey is 1.65. Now we need to find how much volume is required. In both cases, Vx is how much and Vy is how much. Now for that, uh, let us think a bit. So in this, all the volumes are going to change and the voids ratio are changing, right? So which parameter is going to remain constant? The parameter which is going to remain constant is only Vs is going to remain constant, right? Now, how to compute Vs? We have to compute Vs. We have from embankment, we have E is equal to Vv by Vs. From the embankment, we have zero point 0.7 as voids ratio. And we know the total volume, which is 7 lakhs. We need to compute Vs by Vs. Now, if we compute Vs, sorry, if we solve this relation, it's going to be 1.7 Vs is equal to 700,000. Now, Vs is going to be 411,765. It's going to be 411,765 meter cube is the volume of soil solids. So that is not going to change since the assumption is both X and Y have same type of soil, but the state of soil is different. The state of presence of soil is different in terms of voids ratio and uh, in terms of voids ratio. Now we need to calculate Vx. So we know Vx is equal to 0.75, which is equal to V minus Vs by Vs, which is 0.75 is equal to Vx minus 411,765 divided by 411,765. Now Vx is going to be 1.75 times to be 720. 720,000 588 meter cube. The same for EY, it's going to be 2.65 times 411 765. 411 765 into 2.65. It's almost 10 lakh 91,000. BY is going to be 10 lakh 91,177 meter cube. Now, cost of X is going to be 20 into Vx, which is, and cost of Y, sorry, cost of Y is going to be 15 into Vy, which is going to be, that is computed, into 15. It's 163 67659 67659 rupees. For this one, 72588 72588 into 20. It comes to 144,11760. So we know that Cx is less than Cy. So Borrow-Pitt X is more suitable, right? So here in this problem, we have related our concepts to the actual economics of the civil engineering problem, right? Actual field conditions. Now with this, this session comes to an end. So I hope you will be benefiting. Um, you'll be benefiting from these sessions. Those who cannot attend can always follow these sessions in your uh, the recordings and try to solve these problems. And these sessions will be uploaded in YouTube and the links will be shared as I said before. And I expect active participations from the learners, and those who are participating, I encourage them to ask questions and kindly interrupt wherever you are stuck. And those who are watching the recording, you are free to reach out via email in the NPTEL portal. So these sessions will be usually uh, conducted from 5 p.m. to 7 p.m. on Saturdays, and uh, and also today I apologize for some of the network issues which are unfortunate. So even though I have uh, taken sufficient precautions compared to last week in establishing a stable internet connection, but some these things are unfortunate, which should not have been happened. And I forgot to remind you that the next week session will be postponed to Monday, since I'm not available on Saturday next week. So on Monday, 23rd February, 5 p.m. to 7 p.m., we will be conducting these sessions. So this postponement is only for the next week, and it's not for the remaining weeks. So as usual, for the remaining weeks, we will be conducting these sessions in the regular intervals. at the predetermined timings or pre-informed timings. So I hope this session was useful to you. So we will meet in another session in the week 5, and I expect all the learners to uh, watch the video of the contents that is being uploaded in the NPTEL for the particular week and come to this session so that you are prepared to solve the problems. And uh, so from next week onwards, we can expect more numerical. The sessions will be dominated by more numerical questions rather than the theory, which was the case in the past 3 weeks. And you might have observed today's session was slightly introducing numericals to you. So further, we'll be working on several numerical problems corresponding to the content that has been taught in that particular week. So with this, I would like to conclude this session and thank you all for attending. So I will stop sharing the screen.